So we'll now consider the last part of this section on chemical kinetics, where we phenomenologically are describing the reaction rates. And we'll now consider a very interesting reaction, which is known as consecutive reaction. So consecutive reaction. So consecutive, as the name suggests, so it is basically the reactions proceed in a sequential or in a consecutive order. So A is forming something like B, and B is then forms C, something like that. And suppose all of the rates we are now considering as first order. So this is example of first order consecutive reaction. And also the stoichiometries are all equal to 1. So and let us assume we call it as K1 and K2, the rate constants. And the question is how A, B and C vary with time. That we are going to solve. Now at time t, again as before, let us say that it was all A0. So we started with only A0, B was 0, C was 0. At some arbitrary time I have A, B and C. Now first thing first, let us consider dA dt. Now dA dt is very easy to figure out. It is nothing but dA dt will be nothing but, or minus dA dt will be nothing but K1 into A. So that solution is very easy. So A will be, it's a first order decay. A is nothing but A0 into e to the power minus K1t. Now that is straightforward. Now for dB dt, we'll have some interesting situation. Is, if you follow very carefully, it is forming at a rate K1 into A, and it is decomposing at a rate K2 into B. So now we have to integrate, but then we have to eliminate A and B. So now we have a problem in this situation, because the B now contains A also. Now A already we have some form, because we have already solved the A, which is nothing but A0 into e to the power minus K1t minus K2 into B. So that's the equation. Now how will you solve it? Now for that we will use a standard integral. If say dy dx is something like f of x, where f is a function of x, plus g of x into y, then we'll use that y is e to the power integral g of x dx times integral e to the power negative of integral g of x dx times f of x dx. So it's an integral of this multiplied by this dx plus c, where c is the constant of integration. Now let us just use this standard integral and try to figure out what are the terms here. So here y is nothing but the concentration of B, and x is nothing but the time. And now let us see what is fx. So it is fx plus y into something. So this is y. So fx is nothing but K1 A0 into e to the power minus K1t, and gx is just a constant, which is minus K2. You can see it is gx into y. So you can just write the equation. You can just write it here. B is nothing but, you can follow it from here. So I'll have e to the power integral gx dx. So it will be e to the power integral minus K2 dt. Then in parenthesis we'll have integral of e to the power, now there is a minus sign already, so I'm writing it as like this, minus K2 dt. and then fx is nothing but k1 into a0 into e to the power minus k1t, and then I have dt into, and then plus c. Now if we write it down very carefully, if we follow it, that I'm keeping the c right now, so e to the power minus k2 is just a constant, so this will be nothing but e to the power minus k2 into t, and inside bracket I'll have e to the power minus k2t, it will be plus k2t now because there are two minus, and then I have e to the power minus k1t, but I could write it actually, I could write them as together. So, and also there are some constants which I can see, k1 into a0, that I can take out of the integral, k1 into a0 into, I have an integral of e to the power, remember it is now minus k1 plus k2 into t into dt, and then I'll also have a constant of integration. Now you can easily figure that out. It is basically, we could write it as e to the power k2 minus k1, whichever way you like it. So e to the power mx integration is nothing but e to the power mx by c. So this integral will be, if we just write it here, it will be nothing but e to the power, or we can write it in the next page. So just remember it is e to the power minus k2t, that is the first term. So b is nothing but e to the power minus k2t times, now this integral, inside I have some constant k1 into a0, so just write it, k1 into a0 times, I'll have the integrand, which is integration of this, so it will be e to the power minus k1 plus k2 into t divided by minus k1 plus k2. So it will be e to the power minus k1 plus k2 into t divided by minus k1 plus k2, plus I have a constant of integration which is c. Now we can first evaluate the constant. So at t equal to 0, we can figure out the b is 0, because we said that the initial concentration of b is 0. So this thing is also 1, and so what we have here is k1 into a0. This is also 1 because this is now t is 0, minus k1 plus k2 plus c. So I can easily evaluate what is c. C is nothing but negative of this entire number, so it is minus k1 into a0, and we'll have 1 divided by minus k1 plus k2. So that is c. So we can easily rearrange now what is b. So b is nothing but, b means b at concentration of b at any time, any arbitrary time. It will be e to the power minus k2 into t into, now I can take this entire factor as common, we can just take it out, so it will be nothing but I'll just take not the minus sign, I'll just write k1 into a0 divided by minus k1 plus k2, and then inside bracket, so I have taken this out and this out, which was for c actually I'll have minus 1 here, and inside bracket I have e to the power minus k1 plus k2 into t, or we can simplify it, I can actually now move this guy inside this bracket, and then I can get a nice form for minus k1 plus k2. So let us do it. So if I multiply by e to the power minus k2t, So e to the power plus k2t cancels out here. So the first term is e to the power minus k1t, and the second term is minus e to the power minus k2t. So this is the expression for B, and for C, we can actually proceed in the similar way. We can write dc dt and then write it in terms of B, because you remember that this dc dt will be nothing but, because C is forming, so it is forming at a rate of K2 into B, and instead of B you can write this big expression, but that's a very clumsy way of writing. Instead you can just, instead of this way, you can just argue always at any point of time, since I have 1:1 stoichiometry. At time 0, all the concentration was A0, and A0 is being converted to B, and B is being converted to C. So at any point of time, if I had taken this concentration, sum of concentration of A plus B plus C, that will be the sum of the initial concentration, which is A0 plus 0 plus 0, which is nothing but A0. So from there, actually, we can easily figure out what is C. C will be nothing but A0 minus A minus B, and you can now use the values of A and B. A already we solved that A was A0 into e to the power minus k1t, it is just a first order, and then B already we have this big expression. So if you write it down, the expression for C will look like something like 1 minus e to the power minus, or we can actually write it in the next page, because we are going to plot all of them together. So the equation for A was nothing but A0 into e to the power minus k1t. Equation for B was B0 into e to the power, not B0, I mean we just solved it, it's a big one, so we had it as in terms of A0, so it was A0 into, we have K1 by minus K1 plus K2, if you remember that this equation, into e to the power minus K1t minus e to the power minus K2t into e to the power minus K1t minus e to the power minus K2t. And for C, using the material balance that A plus B plus C will always be equal to A0, we can write it as A0 into 1 minus K2 by minus K1 plus K2 into e to the power minus K1t plus, we'll have K1 into minus K1 plus K2 into e to the power minus K2 into t. Now let us plot all these concentrations together on the same plot. So y-axis is the concentration of the species and x-axis is just the time. Now let us suppose we are considering one particular situation where K1 is much larger than K2. So again, this reaction was this, A is going to B and B is forming C with rate constants, first order rate constants K1 and K2. So if K1 is much greater than K2, the plot will look like something like this. So the A actually falls with a steep exponential decay because K1 is much larger, and then B actually initially forms because it is forming from A, and then it will further decay because it is now decomposing into C, and C will slowly rise. Now let us try to explain why the curves are so like that. So this is a curve for A, this is the curve for B, the intermediate. Now B is called an intermediate, and this is the curve for C. So it is as if A is going into C via B, and where B is the intermediate. So this is the only for the constant condition that K1 is much larger than K2. We'll see also the other condition in a minute. Now just think about it. So A is very simple. It is just decaying with minus K1 into T. All right. So let us now try to understand what happens for these curves when the time is very early time, or T tends to 0. Now remember that all these exponential terms, you can write it as e to the power minus x is nothing but 1 by e to the power x, which is nothing but 1 by 1 plus x square plus all the way. Now usually if all these terms are very small, x and x square and all these terms, so then you can think that these terms we can ignore with respect to 1, and then you can actually write it to be equal to 1 if, of course, x is much less than 1. Now you see here when t tends to 0, and also we have a condition like K1 is much larger than K2, so the concentration of the B will be proportional to, you can write it A0 into K1 by minus of K1, because K2 we are ignoring. Now e to the power K minus K1t and e to the power minus K2t. Now t goes to 0 and K2 is also very small, which means now you can ignore the e to the power minus K2 into t, as you can just approximate it to be equal to 1. But e to the power K1t you cannot approximate because t is small but K1 is still large. So I'm just keeping it as e to the power minus K1t minus 1, which you can actually write it as, you could use this minus sign and put it inside. So then it will be nothing but, now let us just write it. So it will be nothing but 1 minus e to the power minus K1t. Now think about it, what is happening. Here it is 1 minus e to the power minus K1t. So A is decreasing with a rate e to the power minus K1t, and B is rising with the same rate. So that's why initially this A and B rates are exactly opposite. So A is forming B and B is forming, B is getting formed, and then B is actually decomposing at a very slow rate. That's why the decay of the B is not very significant right now, at least at the initial part. So it is as if C is just not there, because C going from B to C, the rate constant K2 is much smaller. But however, at a very longer time, what will happen, you can think that this B, we still have the same condition. So K1 is much larger than K2. So the this will be just minus A0 because there is a minus sign. Now if you take the other limit, so you can actually set e to the power minus K2t, this term, to be 0 now because t is very large, and then you can totally ignore that term, and then you can actually not this term, sorry, this e to the power K1t term, that you can totally ignore because K1 is large and t is also large, so it is going to e to the power minus infinity. So it is you can totally ignore it. It is as if it is 0, and then you have the second term, which is e to the power minus K2 into t. So together you can write it. There is a minus sign also here. So this minus sign and that minus sign, you can together write it as e to the power minus K2t. So in the long time, B is decaying with its own rate constant, which is basically B is forming into C. And at that rate, C is also growing. You can see that. Now, let us consider the other limit. So these are basically the two limits for this condition. But we can also think about when K2 is much greater than K1. And then we'll see that there is a very interesting situation. If K2 is much greater than K1, let me first plot it, and then again qualitatively, not qualitatively, quite quantitatively try to describe why the nature of the curve is like that. In that case, A will decrease very, very slowly. The concentration of the B will rise and then will become very, very steady, and then but rise a little, and then we'll have a C which will first go and then grow. Now what is happening here? Again, we can approximate that at t tends to 0. Now remember that K2 is much greater than K1, so I'll have always look at the B equation. So the B equation will be A0 divided by K1 by K2, because I'm ignoring now K1 with respect to K2. And then inside parentheses I have e to the power minus K1t and e to the power minus K2t. Now we'll follow the same logic. If K2 is very large, you can think that K1 is very small, so e to the power minus K1t can be approximated to be equal to 1, because K1 into t is a very small number, and if x is a very small number, e to the power minus x is 1. And then minus, we have e to the power minus K2t. Now think about it. So this is also in growth, just like the earlier case. However, look at it very carefully. So when we have this kind of situation, so initially the B will rise, of course, but then sooner or later what will happen is that we have it, just 1 minute, we have K2 is much greater than K1, so that's why we are ignoring this term, making it to be 1. Yeah, that is perfect. And when t is very large, then B, as before, will be A0 into K1 by K2, and then we'll have e to the power minus K1t, because now what is happening, this K2 into t is very large, so e to the power, it is almost e to the power minus infinity, so that is going to almost 0, and then we'll have just e to the power minus K1t. Now let us look at the nature of the curve. Think about B. So B is actually now growing as e to the power minus K2 into t, not as e to the power minus K1 into t. So earlier A was forming into B, and that was basically the driving force, but here you can see that B is actually decaying with e to the power minus K2t. So the growth of the B was initially e to the 1 minus e to the power minus K2t, but the growth is not very large. Why? Because you see there is a factor which is K1 by K2. Since K1 is much less than K2, so this curve did not rise to a very great height. So it just had raised a little bit and then trying to decay. And in the very long limit, you can see I have a very small factor which is always there, K1 by K2, and then I have e to the power minus K1t. But what is K1? K1 is a very small number, so the decay will be also very slow. So under this condition, we can say that the intermediate concentration is such a way, it is varying, that it is almost 0, which means the intermediate is not varying over time. Remember that we do not have space here, so let me just write it as here. So it is at A0 to K1 by K2 into e to the power minus K1t. That is okay. I'm just removing this part because my picture is blocking that section. So we can write it, and then C actually grows. And A, look at the A curve. The curve of A actually decays much slowly because A is nothing but e to the power minus K1t, but now K1 is much small, so A decay is very slow. And B, not B, the C actually grows with a rate which is K2 into T. And K2 is large, so that's why C actually grows much at a much higher rate than this curve, where actually initially C did not grow much. So we have a period where actually C now builds up, this period, and that period is known as induction period. So during the induction period, the concentration of B is just building up. When not B, the product C is building up, when actually B was rising, but then all of a sudden the B becomes almost steady, condition. And why it is steady state, it is we can actually easily see it from the curve. It decays at a very, very slow rate, e to the power minus k1t, and in a very long time limit, in the t tends to infinity limit, and under this condition where k2 is much, much greater than k1. So thus we see that the nature of the curves in a consecutive reaction varies greatly if you take k1 much, much greater than k2 or k2 much, much greater than k1. And we can actually now have a very interesting analogy between these two rates. So what is happening, suppose I have a bucket. I have actually 3 buckets, and I'm basically suppose this is A. Initially I pour some water here, and then the bucket B and bucket C are empty. This is A, this is B, this is C. Now suppose I punch a hole here, in the sense that I punched a hole like this, which means I have K1 much, much greater than K2, means the water is pouring here in the B, but B also has a hole, but that hole is much smaller. So what will happen? Water will first fill in the B, and then slowly this will come to fill in the C. So in the long term, of course, everything will be C, but in the very early time, you will see that it is only filling up B, but slowly B also transfers that water, but at a much slower rate, because now that K2 is much slower than K1, and that's what exactly you saw, that A1 is filling here, A1 is decaying, and B is actually growing with the same rate. But after some time, actually it starts decaying, when actually A also has completely consumed, and then B is only decaying, and then C also rises at the same rate like the B is decaying. Similarly, on the other extreme, when I have K2 much greater than K1, what will happen? I have a small hole here, the water is coming, and then it is filling here, but as soon as it is filled, I have a very, very larger hole here. Immediately the water gets passed and fills the C. So what I'll see here, that this water level will be a little bit high always, but as soon as it is filled in, that actually gets passed to the other bucket, because now K2 is much larger than K1. So you see that initially the B has a rise, but then it just doesn't change, because as soon as it is filled in, it is decaying, and quickly the C actually takes over. It just goes above B very quickly, and A actually is decaying very, very slowly. The reason is A has a very small hole. So this is a nice analogy you can think of for a consecutive reaction, that water is being transferred from one bucket to the other bucket and eventually to C. So eventually all the water will be transferred from A to C, but through an intermediate bucket, which is the B bucket. So this B is an intermediate, and in many, many chemical and biological reactions, these intermediates has to be studied to understand the reaction mechanism, and the kinetics of the intermediate is very, very important, where we can actually understand the how the intermediate varies with respect to time. And we see that under conditions like when the first rate is larger than the second rate, or the second rate constant is larger than the first rate constant, we can have very, very different situation. So to summarize what we actually studied in this intersection on the first part of chemical kinetics, we just defined how we can express the rate equation. We also discussed how you can express the rate equation as a function of the concentrations, that we call as rate law. And then we integrated it. We wrote it in a differential form, and we showed how to integrate the rate law for various reactions like first order, second order, and nth order, second order with two different species, and many other ways. And then we talked about interesting situations if we have reversible reaction, or if we have competing reactions like this, or at last we also talked about the consecutive reactions. So in the next lecture, we'll discuss about mechanism. So we'll use all these concepts which we have built in so far, and then we'll see how using these concepts of the rate constant we can actually propose a mechanism of a reaction or a composite reaction which is actually can be split into many elementary reactions, and if we add up the overall rate constant on the rate log actually mimics what we observe experimentally. So we can actually propose many different mechanisms, and meaning that many different mechanisms can explain the same reaction, but we'll choose actually very intelligently which one actually can be the most common or most reliable mechanism, and we'll use some approximation how to do it. We'll use two approximations, steady state and equilibrium approximation, or rate determining state approximation, which we'll be discussing in detail in the next lecture. Thank you.